All right, so today we have Niklas Garner who will tell us about BRST complexes of graded unitary VOAs. Take it away.
Great. Thank you for the invitation to speak. It's a pleasure to get to tell you about some of my research on such a spooky day. The story I wanted to tell you about is some recent work that I did with Chris Beem, building on some of the physically inspired mathematics that he's been doing with collaborators. And just as a brief overview of the sort of thing that I want to tell you about, it is sort of as follows. The punchline, in some sense, is that unitarity is really powerful. I don't think I need to convince anyone here about that. But when we're talking about supersymmetric quantum field theories, and in particular, twisted supersymmetric quantum field theories, unitarity is almost always lost. There isn't much unitarity that survives when we're taking representatives of cohomology classes of states. And so it's hard to leverage those tools when we're studying twisted quantum field theories. But in some nice instances, there are imprints of this unitarity on the twisted theory. And this is brought to bear in this recent paper of Chris and collaborators in the context of the 4D superconformal field theory vertex operator algebra correspondence. And in this context, what they were able to develop is a notion of unitarity for vertex operator algebras that in some sense reflects the unitarity or encapsulates the unitarity of the parent superconformal field theory that you twisted to get to this vertex operator algebra. And so this is one of these special instances where we can actually leverage the powerful consequences of unitarity in a setting that is totally algebraic or in twisted quantum field theories. And so the thing I wanted to tell you about today is the constraints that we gleaned by imposing graded unitarity on the vertex operator algebras that come from superconformal gauge theories. And a lot of the techniques that we were able to implement, or the ideas behind the techniques, were borrowed from the theory of Kähler geometry. And I'll explain that when we get there. But the basic sort of underlying principle is that we want to combine this notion of graded unitarity with the structures present in superconformal gauge theories and their vertex operator algebras, and deduce consequences of these vertex operator algebras, or constraints and structural properties that these vertex operator algebras have. So what I wanted to start with, because I'm not really speaking much about quivers, I want to provide a little bit of background. The thing I wanted to start with was a review of this SCFT VOA correspondence from back in the day. And the setting, or the starting point, is the vector space of local operators in my four-dimensional n equals 2 superconformal field theory. And this is going to be the vector space of local operators of T at 0. And of course, being a superconformal field theory, this vector space is acted upon by the n equals 2 superconformal algebra. And when you complexify it, this is something like SL4/2. And there's some real form of this, SU2,2/2, that acts via unitary transformations, but that's not so important for the moment. One of the salient features of this action is that I can decompose the representation space, this vector space of local operators, into selection sectors of given energy, spin, R symmetry, weights. And so this size of the carton of this super Lie algebra is 5-dimensional, and the quantum numbers are the ones I just said. So we're twisting we have in the background two preferred supercharges that I'll call Q1 and Q2, and I've written them in terms of the standard expressions for the superconformal and Poincare supercharges. The structural form isn't so important, but the properties that they satisfy are as follows. The first one, of course, if we're twisting, we want things that are square zero. This isn't going to be one of those equivariant type of twists. This is one where my supercharge is genuinely square to zero. The second thing is that there's two copies of SL2 that commute with these supercharges. And these generate holomorphic and anti-holomorphic conformal transformations on a copy of C inside of R4, which I think of as C2. But one important feature is that the anti-holomorphic coordinate transformations aren't just L bar. It actually includes this R symmetry rotation as well. And this stems from the fact that translations usually don't commute with superconformal charges. And same thing with the rotations and dilations on the anti-holomorphic side. And this inclusion of the R symmetry is what's used to compensate for that fact. But the next crucial feature is that these anti-holomorphic conformal transformations are actually exact. So when I look at the cohomology with respect to, say, Q1 or Q2, it's not going to depend on these anti-holomorphic coordinates modulo this translation, including the R symmetry. But these these L hats, which you should think of as generating the anti-holomorphic coordinate transformations of my complex plane, are exact. And so correlation functions of closed operators aren't going to depend on them. And then, unfortunately, Q1 and Q2 don't anti-commute with one another. They will anti-commute to some combination of U1R and a generator of transverse rotations to this copy of C inside of C2. But that's not the end of the world. It's sort of a feature rather than a bug. Okay, so when we're looking at cohomology with respect to these supercharges, there are going to be some natural operators that survive. These are sort of the ones that saturate the BPS bound, given by being annihilated by this collection of Q's and S's that I have up above. And the consequences that you see, the BPS conditions are two constraints on the quantum numbers that I've written here. And the class of operators that satisfy these constraints are called Schur operators. When I'm looking at a unitary quantum field theory, n equals 2 superconformal, this implies that these are actually highest weights with respect to the SL2R symmetry. And so the SU2R index, when I write it in terms of a bunch of doublets, is always going to be 1s for these operators. Okay, so I mentioned that we have this action of L and L hat that commutes with the supercharges, and translation in the holomorphic or in this complex plane are generated by L minus 1 and L hat minus 1. And so we can move operators around using those translations, those infinitesimal translations. We just exponentiate and conjugate. But because of this inclusion of the SL2R, it's not like a genuine translation. It's what's called a twisted translation. And the form of the twisted translated operators is written here. So I have my favorite Schur operator, O1111, and I want to place it at some point z and z bar in the complex plane. And I do that by just conjugating by the action of these L-1 and L-1 hat, weighted by z and z bar. And what you end up finding is that you have actually a sum of operators that come up weighted by powers of z bar correlated with their SL2 weights. But the important part of all of this is that when I look at the cohomology class of one of these operators, twisted translated to a point z bar, it's actually independent of z bar. And when I look at correlation functions of these, there'll be singularities as they become close to each other, but the singularities dependence on z bar is going to be exact in cohomology. And so the structure that these local operators are going to have, or rather their cohomology classes, is that of a vertex algebra. Or you should think of this type of chiral algebras that you see in two-dimensional conformal field theory or chiral conformal field theory. But there's also another word that you could have put in there, vertex operator algebra. That's part of this correspondence. It's not just vertex algebras. And this is showcased by the fact that there's actually a stress tensor in this collection of operators that is represented by this component of the SU2R current multiplet. So the collection of these twisted translated Schur operators forms a, or rather their cohomology classes, forms a vertex operator algebra. And this SCFT VOA corresponds is some map from superconformal field theories with n equals 2 supersymmetry in 4 dimensions to vertex operator algebras via this construction. Okay, but there's more. There's always more. Because I put 2 constraints, or the BPS conditions on these Schur operators impose 2 constraints, rather than the 5 Cartan elements that I had above, this vertex operator algebra is naturally triply graded, or at least the vector space underlying it is triply graded. And it's triply graded by the conformal weight, H. In terms of the quantum numbers from before, it's a half E plus J1 plus J2. And then 2 R symmetry weights. So the vector space here is naturally triply graded. But as we saw with these twisted translated operators, the operators I put at different points in the plane other than 0 are sums of operators with different R charges, capital R charges. And so the vertex operator operations, like the operator product expansion, isn't going to be a sum of operators of a fixed R charge. And so the vertex operator operations, for example, when I take a contour integral weighted by z to the n or whatever, the operator I get on the other side isn't going to be homogeneous in R charge, or at least it's not guaranteed to be. But all is not lost, because rather than being an additional grading on the vertex operator algebra, it instead leads to filtration, which is sort of the next best thing. It's not a grading, but it's very close. And I'll have a specific expression for what this filtration means. But it's not just any old filtration, it's actually a special kind of filtration called good. And a good filtration is one that satisfies this condition that I wrote here, which says if I take one operator in the R1 filtered component and a second operator in the R2 filtered component, and then do my usual contour integral weighted by z to the n of O1 around O2, this is going to be some other operator in V, and the statement that it's a filtration says that it belongs to the R1 plus R2 filtered component. This goodness filtration, this goodness of the filtration, rather, imposes something yet more, which says that if I look at the negative modes, the ones with positive conformal weight, or well, sorry, with weighted by positive powers of z in the operator product expansion, the singular terms rather, then this actually has to decrease the filtration. And this comes from the fact that the OPE of Schur operators by themselves is going to be regular. And so the type of filtration that you get in these VOAs coming from the SCFT VOA correspondence have a filtration that is good. One nice feature about these good filtrations is that when I look at the quotient of the successive filtered components, this is sometimes called the associated graded of a filtration, then it's naturally equipped with an algebraic structure of its own called a Poisson vertex algebra, or vertex Poisson algebra, or Poisson algebra, depending on who you talk to. But this isn't some scary thing. It actually has its own physical meaning. And the algebra of operators, or this sort of Poisson vertex algebra, can be thought of as the algebra of operators in the holomorphic topological twist of this n equals 2 theory, also called the Kapustin twist. And so this filtration allows me to have some extra information that allows me to take some sort of classical limit, if you'd like, where this classical limit is sort of going from the quantum vertex operator algebra to a semi-classical or quasi-classical Poisson vertex algebra. The vertex algebra is some sort of quantum non-commutative thing, and the Poisson vertex algebra is some commutative thing but has a Poisson bracket. If you're used to the description of these vertex operator algebras in terms of an omega background, this quotient by the filtration, or this associated graded, is something like turning off the omega background. So in that sense, this omega background is a quantization procedure. And taking this associated graded is how you go from quantum things to classical things. Any questions so far? This is most of the background that I was going to describe. Okay, great. So let me give you some examples of this this correspondence. The first two are going to be free field theories. The first one is the free hypermultiplet. In this example of a free hypermultiplet, you get a vertex algebra known as the symplectic bosons, also called the beta gamma system, if you like that name for it. It's got two generators, Q and Q tilde, and their operator product expansions. Singular term is just a 1 over Z, minus 1 over Z, depending on your conventions. So this is some sort of bosonic version of a Majorana fermion, or complex Majorana fermion, if you like. The operator Q and Q tilde correspond to certain scalars in the hypermultiplet. And the quantum numbers I was telling you about before are given here. Both of the hypermultiplet scalars have R charge a half, SU2 R charge a half, U1 R charge 0, and when you look at this conformal weights, the scaling dimension is a half, or sorry, it's 1, and then you have a half in front. So H is 1, H is a half, capital R is a half, and little r is 0. Next example, another free theory. You get what's called the symplectic fermion vertex operator algebra. This one also has two generators, but now we put a second order pole between them. you can kind of think of this as a fermionic analog of the Heisenberg vertex algebra, if you like. And the quantum numbers are given there. They've got conformal weights 1, coming from the scaling dimension 3/2 of the fermions, and the spin being 1/2. Capital R is 1/2, and little r is plus and minus 1/2, where that guy's got plus 1/2 and that guy's got minus 1/2. And then the next, the sort of most interesting part of these examples is what happens when we look at a gauge theory. Namely, we have some matter, quote unquote, theory that we want to gauge. The vertex algebra that I get from this is often written like this, which is a bit of a mouthful, but you should, if you'd like to read what this is, it's relative semi-infinite cohomology with coefficients in V matter, which if you've never seen it before, I don't blame you. So let me explain a little bit about what this is. The first ingredient, of course, is the to be gauged theory's vertex operator algebra. And that's this thing I'm calling V matter. And if I want to gauge it, then it has to have some flavor symmetry at a suitable level for it to be a superconformal gauging. And at the level of the vertex operator algebra, this says that it has some affine currents, and the level of the affine currents is required to be minus twice the Coxeter number, or minus twice the critical level. And this, when you trace it back to the parent superconformal field theory, is precisely the statement that when I gauge, the beta function is 0. Once I have this vertex algebra with currents, I throw on a BC ghost system valued in my Lie algebra G. If you don't remember what that is, it looks like this. I've got some C ghosts valued in G. I've got some B ghosts valued in the dual, and they have a 1/Z pole in their OPE. There's a special field in this vertex algebra that I call calligraphic Q. Sorry, that should be a Q tilde, my apologies. That includes this current J together with a current built out of the BC ghosts. And then we look at the 0 mode of this current. C has conformal weight 0, B has conformal weight 1, and the assertion that the level is this -2 H check translates to the fact that Q tilde has a regular OPE with itself. And so this 0 mode squares to 0. So we can take this V matter plus BC ghosts and then take cohomology with respect to this Q tilde. And if I were to do that, then that would be the semi-infinite cohomology. But what we want is actually the relative semi-infinite cohomology. And so we have to do a little bit more. A little bit more is to restrict to this subalgebra. Relative means that I impose gauge invariance by hand. So gauge invariance for the finite part. So I look at states that are annihilated by J0. Oh, sorry, this should be, sorry, this shouldn't just be little J0. This should be the sort of combination of both of these things right here. So that should be the thing right here. My apologies. And they also are annihilated by the 0 mode of the B ghost. What this is really doing is this thing says I can't have any C's, but I can have del C's. And so what I'm really looking at is symplectic fermions, that thing we saw above, tensor the matter BOA, and then we take the G invariance of that thing. And to get the symplectic symplectic fermions, what I do is I throw away C and I keep del C. So I have G copies of the symplectic fermions. I tensor it with my matter VOA, take the G invariance, and that's most of the way there. The thing that we have to do now is take cohomology. This is a relative semi-infinite cohomology after all. And the cohomology that we take is realized by restricting this Q tilde I had up here to this subalgebra. And so the relative semi-infinite cohomology is just a long name for restricting to the subalgebra and then taking cohomology with respect to the supercharge restricted to the subalgebra. And if you like modes, here's what it looks like in terms of modes. It's kind of a mess, but it sort of is what it is. I have the thing that was previously the CJ that's showing up right here. This structure constant I've moved around a little bit using a metric on my Lie algebra. That's secretly what happened here, if you are paying attention. And then I've got 3 etas coming from the CCB term. But you'll notice that in this symplectic fermion example up here, the plus and minus are, in some sense, just as good as the other one. In particular, this thing is called symplectic for a reason. It actually has a symplectic automorphism group where these two transform as a doublet with respect to the symplectic group. And from this presentation of this subalgebra, you can see that it still has this sp2 action. And in particular, there's actually 2 of these supercharges, Q, I'm going to call them Q plus and Q minus, where I exchange the roles of eta plus and eta minus in this expression. And these guys transform as a doublet with respect to this sp2 that rotates eta plus into eta minus. And so this pair of supercharges Q plus and Q minus is some vertex algebraic incarnation of the fact that I had 2 supercharges that I could have looked at above. In this intro bit, I was saying there's Q1 and Q2, and either one of them is just as good as the other for computing the cohomology. And the vertex algebraic incarnation of that statement, at least at the level of these gauge theories, is that there's actually 2 supercharges or 2 nilpotent differentials that I can use to compute the same thing. So then this is the type of thing that we want to be looking at least for the things that I'm interested in this talk. Okay, so now to get to the first words in my title, or well, I guess I've done the on BRST complexes of, now to get to the graded unitary vertex algebras. This is, as I was saying earlier, based on earlier work from earlier this year with, not with me, but by Chris and Arash, Madalena, and Leonardo. And the basic idea is that unitarity of the parent 4-dimensional superconformal field theory imprints itself on this vertex operator algebra by way of a naturally defined inner product. So how does this work? Well, the basic idea is that, well, how do I get an inner product on local operators in a superconformal field theory or conformal field theory? Well, I put operators at 0 and infinity and compute the 2-point function. This is just how you do it. And so that's what we're going to mimic here, and how this group defined the notion of graded unitarity, although you have to be a little bit careful with how this works. But okay, how does it work? In radial quantization, if I want to look at the norm of a state, or operator in this case, O, what I do is I take a 2-point function, put the complex conjugate at infinity, maybe I put it at some finite distance and then take a suitable limit. And this is my 2-point function. And therefore the inner product of the state with itself. If I'm looking at Schur operators, then I have this constraints on quantum numbers. And when I rewrite them in terms of the ones I was telling you about before, they turn into this sort of expression where the J's you can see turn into, sorry, the Z's turn into the E plus J plus J1 plus J2, and Z bar has just the R charge in it. Okay, well, it's still not that useful yet. But the problem in some sense is if we want to connect this to vertex algebra land, O star isn't sure if O is sure. And so what we need to do is turn O star into a sure operator somehow, or relate it to a sure operator. And the way to do that is by rotating in the SU2R multiplet. I was saying earlier that this guy is a highest weight vector of some SU2R multiplet. When I take its adjoint or its complex conjugate, that operator is the lowest weight in a different multiplet, or presumably in a different multiplet. And what I can do is then rotate it back up to a highest weight vector, which will then be sure. And this O tilde operator that I have here is precisely the operator that I can get by doing this rotation. And then I stick on a factor of I to the 2R because of conventional reasons. Like when you look at this operator, it's the one that sort of has I's on the diagonal, or sorry, anti-diagonal, sorry. And this is just stoking up those factors of I when I do this rotation. So I then take this operator O tilde and do my favorite twisted translation. And crucially, O star appears at the bottom of this expression. And sort of maybe magically, if that's the way you like to think, it has this factor of Z to the 2R showing up as well. And so what you see is that the inner product of O with itself can be realized as just a limit Z to the 2H of O tilde with O. And so this map that I came up with, or well, I didn't come up with it. This group of authors came up with it, that sends O to a rotated version of its complex conjugate, is an antilinear map on sure operators. It also squares to -1 to the 2R. And so this is one of the ingredients that we'll need in defining our notion of unitarity at the level of vertex algebras. And this, in sort of vertex algebra land, is some antilinear map that satisfies this nice condition that says when I look at rho applied to the action of O1 on O2, then I can read it off or realize it as the action of the rho applied to O1 on rho applied to O2. And this is just some conventional factor coming from complex conjugation of fermions exchanging orders and so on. And so this conjugation operation is going to be one of the ingredients that we'll need in defining graded unitarity. We also had this factor of 2i, or sorry, I to the 2r showing up. And so we'll need this thing that I'll call sigma, which is just multiply operators by a suitable power of I, depending on their R charge. And with these two ingredients, the inner product of O1 and O2, as viewed from the parent SCFT, can be realized wholly in vertex algebra land by taking this 2-point function of a sigma rho applied to O1, and then bringing it to infinity and stripping off a suitable factor of Z and doing it. So this expression here is sort of the vertex algebraic incarnation of this 2-point function of local operators I get in the physical theory by placing one at 0 and one at infinity. And I should stress that if I didn't have this sort of rho and sigma, then this is the sort of natural type of 2-point function that you would have in ordinary 2D CFT. You just take one operator, you place the theory on P1, for example. You put one operator at 0, you put the other one at the other pole of P1, sorry, S2, and you compute a 2-point function. So in some sense, the extra frilly bits are just the thing that translates from 2D to 4D. But otherwise, you're doing the thing that you thought you should do in conformal field theory. You just take a 2-point function to define your inner products. So we can abstract this a little bit. I was sort of forecasting this in the previous slide. There's 30 pieces of data that go into this. The first one is this non-degenerate invariant pairing that you can think of as coming from looking at these 2-point functions that I was talking about. So like if I had stripped off this rho sigma, this invariant pairing is the 2-point function in earnest, sort of only seen from the vertex algebra. The second ingredient that we saw earlier was the filtration. So in addition to this invariant pairing, we'll want a filtration around, and it'll be good if it comes from 4D. So we want a non-degenerate invariant pairing together with a good filtration, and the filtration will also be non-degenerate in the sense that if I restrict this pairing to any one of the filtered components, it remains non-degenerate. And one consequence of that non-degeneracy when restricted to filtered components is that I can do a Gram-Schmidt type procedure and make this filtration a grading of vector spaces. So in principle, I only have a filtered vector space. I can use Gram-Schmidt to peel off parts of lower R charges and get a definite R charge for my states. And so we have this pairing, we have this filtration, and then we also need this rho operation. Again, sigma is just determined by the grading. And so once I have these two, I have a grading and hence sigma. Now I need my conjugation rho. And I require that for this to be a graded unitary vertex algebra, this invariant pairing that I wrote before, where I stick a rho and a sigma into this invariant, this circle bracket, it's a positive definite inner product. And you can also show that it's a skew Hermitian as well. And so this is the sort of nice inner product that we'll want to impose on our vertex operator algebra. This one that comes from 4D superconformal field theories. It's a bit of baggage, but it is what it is. But we can take this abstract structure and then prove some things about it. So one of the things that we can prove is this result we called shortening, which says if I have an operator of R charge R, I can look at a mode of that and then write it in its homogeneous components. As I said, ON doesn't have a definite R charge generally, but it can only decrease R charge. And so this sum is in terms of homogeneous components with R charges less than or equal to the R charge of the state. And shortening says that if R prime is less than R's negation or negative R, then this state, or sorry, this component of the mode has to be 0, which is exactly what we wanted when we're thinking about these twisted translated states. We saw that they were just sums of operators sitting in the same SU2R multiplet, and spins in SU2 multiplets go from the highest weight to minus the highest weight. And this shortening condition says that this decomposition into filtered components, sorry, graded components, naturally respects that type of structure. Namely, I only have operators that can increase R by the R charge by R or decrease R charge by R. And that's exactly what we would want from this twisted translated story. The next thing that we can show is that this is actually truncated, namely the space of states with R charges that are negative is necessarily empty, or well, there's only the zero vector. And this is again what we sort of expected from physics because, well, if I'm looking at highest weights of SU2 representations, they better not be negative if they're finite dimensional representations, which they always are in these contexts. So this is, again, something totally expected from four-dimensional physics, but it's actually a consequence of this structure. The sort of juicy one that we didn't really expect to be able to show, but ended up being able to show, is what we called graded unitary spin statistics. I don't need to tell you what spin statistics is, but graded unitary spin statistics is some statement that says if I have an operator of R charge, definite R charge in conformal weight, then the fermionic parity of the operator is determined by H and R. And so this isn't like usual spin statistics, which says H and conformal weight are tied to each other. We have capital R showing up as well, but you should think of this as some version of spin statistics that correlates conformal weights and capital R charges, SU2 R charges, with fermionic parity. And again, this is something that you sort of expected from physics, if you think about it a little bit, because in n=2 superconformal field theories, the Schur operators little r is the same as these guys mod 2, and moreover correlated with the fermionic parity of the operator. And so in hindsight, it's not so surprising, but it's a neat little consequence of this structure. And then the fourth thing that I want to mention is some useful computational tool, which says, okay, if I have a quasi-primary operator, then the adjoint of one of its modes can be made very explicit. It involves adding some factors of I to its various homogeneous components and taking a mode of its row conjugate. I also have to throw on a factor of e to the I pi h, but okay. All right, now we can actually maybe do some things. What I want to do is give some explicit examples, and then we'll get to the juicy bits. I'll go through this pretty quickly in light of time. Maybe I'll just go through the whole thing. Yeah, I'll just do these two simple examples. This is what rho looks like for free hypers and free vectors. And the corresponding adjoints of these, the modes of my fields are given here. The thing I wanted to bring your attention to is that if I was looking at one of the creation modes for my hypermultiplets, it just gets translated to an annihilation mode of the other hypermultiplet. And so this is the usual type of thing you might have expected, where the adjoint of a creation mode is an annihilation mode. Surprise, surprise. Same thing is true with the symplectic fermion example. The adjoint of a creation mode is an annihilation mode. So not so surprising there. It's sort of what you might have wanted in your heart of hearts. And now I wanted to get to the real thing that we wanted to study, which was combining graded unitarity with this gauge theory example. So we're going to assume that we have a graded unitary vertex algebra, V matter, and it's got currents at the right level to do this construction, that I have superconformal gauging. We also need to put some additional sort of physically motivated constraints. The first one says that these conjugation operations are compatible with the fact that I'm looking at the compact real form. In some sense, when you're looking at this antilinear map rho, and you restrict it to some flavor symmetries, these types of antilinear automorphisms of Lie algebras are correlated with choices of real structures. And this requirement is just saying that I'm looking at the compact real form, which is, of course, the thing that we would want from physics. And if you take that adjoint thing that I wrote above and apply it to J, then the adjoint looks like this. The second thing that we're going to pose is that J has R charge 1 and little r 0 and h equals 1, of course. And again, this is physically motivated. It's not required to be true in vertex algebra land, but it's something that we impose because, well, for one, the machine doesn't work otherwise, but two, it comes from physics. And the shortening condition that I was mentioning and the goodness of the filtration say that some of the modes have much simpler decompositions in terms of its components in the homogeneous decomposition. So the goodness of the filtration says that the positive modes of J can't increase R charge. And then if you look at the adjoints, then you find that some of the negative modes can't decrease R charge either. The reason, in some sense, why we wanted 1 is because then we get a natural graded unitary structure on this tensor product. The reason that we wanted 2, well, besides the fact that it's physical, is that I can then take Q and split it into components of R charges plus and minus a half. If you go back to that expression for Q in terms of etas and J's and so on, and then start writing it in terms of its homogeneous components, you find that it's only plus and minus a half. And I'm going to call them Q and S because, well, that's what they were called in the physical theory. And then you compute. What do you compute? Well, you compute the adjoints of these operators, and you find that Q is sent in S, which is how Poincare supercharges are mapped under radial quantization. You find that the Q's are square 0, the S's are square 0, and some nice things as well. And then we'll use that in this next bit, where what we want to do is then start seeing what the consequences of these various results are at the level of the vertex algebra. And so we're going to assume we have all that structure from above. If you write the Q's as a doublet like that, and you write their adjoints as Q bars, then the relations that I wrote on the previous slide translate to this collection of relations here. And you should, or one way to read this is as the n equals 4 super quantum mechanics algebra, where you have 4 supercharges, Q alpha and Q bar alpha, and a Hamiltonian that I'm calling delta. And so these graded unitary vertex algebras that come from gauge theories have an n equals 4 super quantum mechanics action. And it's unitary. Moreover, there's this SP2 that I was telling you about before that rotates the Q plus into Q minus. That's what's going on here. And it's also a nice unitary action in that it plays well with the adjoints. That should be lowered. And if you've seen n equals 4 super quantum mechanics, you know that the types of manifolds that you can have in n equals 4 super quantum mechanics, at least in one flavor of it, are compact Kähler manifold targets. And so, said differently, the types of structure that you should expect in this looks a lot like the differential forms on a compact Kähler manifold. And the analogy says that Q, Q bar, and delta corresponds to the de Rham differential, its adjoint with respect to the Hodge inner product, an operator called DC, which is just like del minus del bar, DC's Hodge adjoint, and the Hodge Laplacian. I called it delta because it's a Laplacian. And the pi, L, and lambda also have a sort of reason for existence in Kähler geometry. Pi measures form degree. L is wedged with the Kähler form, and L's adjoint, which is lambda, is the adjoint of wedged with the Hodge form. Or sorry, the Kähler form. And so the last few minutes, I wanted to capitalize on this analogy and try to use results in the theory of Kähler manifolds in the context of these graded unitary vertex operator algebras coming from gauge theories. And so the first bit, I realize I have too much stuff, but the first bit is that, well, things that are harmonic are killed by all four supercharges. Surprise, surprise. If something is not harmonic, not killed by delta, but it's still killed by two of my supercharges, then O sits in a multiplet like this. This is sometimes called the quartet mechanism if you have studied 2D superconformal field theories. The exact same phenomenon happens there in like 2-2 superconformal field theories. And the reason why I wanted to mention this is because there's not much we can do with Q bar in the world of vertex algebras. It's not like a nice map at the level of vertex algebras. It doesn't play well with the vertex algebra structure, but you can distill from this analysis a very powerful result, which is called in Kähler geometry, the del bar lemma or DDC lemma. And we called it the Q minus Q plus lemma because we're not that creative. But what it says is if I have an operator that is annihilated by both of my supercharges and exact for one, and I know it's exact for one, then it's actually exact for both. And it's moreover exact with respect to Q minus times Q plus. And the basic statement is that this is sort of my operator that I can be annihilated by both Q plus and Q minus. And I know that there's something that makes it exact. Then I can translate all the way back here to come up with my operator O tilde. So this guy is in some sense O tilde in this picture. Okay. And this Q bar lemma is sort of the formal gadget that we need to prove the main theorem that I wanted to showcase, which is some statement in the world of the homotopy theory of Kähler manifolds transported to the world of vertex algebras. And let me just put it up here. It's due to Deline, Griffiths, Morgan, and Sullivan from way back in the day. And it says that the homotopy theory of Kähler manifolds, compact Kähler manifolds, is determined entirely by their cohomology. If you know things about homotopy transfer and Massey products in topological spaces, this result says that there are no Massey products. Everything that I could want about the homotopy theory of this space is determined by just the cohomology. There's no higher order operations. And the same is true in vertex algebra land, and I can share the details of some of the proof if you're interested, but in light of time, maybe I won't. The thing I wanted to end with was some other things that I didn't have time to share, which I knew I wouldn't have time to share. The first one is that, of course, if we believe that graded unitarity should be something that is true for all vertex algebras coming from 48 n equals 2 SCFTs, then the cohomology should also have a graded unitary structure. And one of the results that we proved, but I didn't have time to talk about, was the fact that this is actually the case. And one nice consequence of this is that it's true for all superconformal gauge theories. Like I told you how to do it for hypermultiplets. This result says you can do it for any Lagrangian gauge theory. Notoriously, the R filtration is hard to do or hard to contend with in any interesting interacting theory. And this result says that the cohomology of this supercharge, the VOA I get from superconformal gauge theories, are indeed graded unitary as expected. The second one is sort of one of the main things that we wanted to prove, which said that if my gauge group is actually a product of two different gauge groups, then I can first gauge G1 and then gauge G2, or G2 and then G1, or I can gauge them both at the same time. And the result is the same, regardless of which way I do this. And this is some Vertex algebraic incarnation of the fact that gauge couplings are exactly marginal. Namely, I could start at the infinitely weak coupling point and then turn on G1's coupling to get to the first quotient. And then I could turn on G2's coupling to get to the second quotient, or I could turn them both on at the same time, or I could do it in the other order. And one consequence of formality is that the vertex algebra reflects this observation. We can also extend this notion of formality to the Hall-Littlewood chiral ring. If anyone's interested, I can tell you more about that. Another useful thing is that the USP2 automorphism that I was telling you about before actually survives at the level of cohomology. And in the world of Kähler geometry, this is sometimes called the Lefschetz SL2. It also works here, but we actually get something better, which says that for each factor in the gauge group G, we have this USP2 automorphism. There's similar story to be told in 3D n equals 4 BRST complexes. So if you look at the story of Gaiotto and Witten, these types of BRST complexes show up in a-twisted 3D n equals 4 theories. And our results actually can be transported, although with some minor tweaking, to that setting as well. I wanted to mention that there's some still lingering questions. The first one is, there's some weird instances where many of these copies of USP2 combine to a yet larger symmetry group. For example, in class S examples, this G is meant to be the genus. There's empirical evidence that suggests that they have very large automorphism groups. And so one question is, how does it happen? Or why? It should be some physically motivated thing, but what is it? The last question is like, okay, what is this USP2? I was telling you that it's something that rotates the symplectic fermions into each other, and these correspond to gauginos. The weights of this USP2 are actually U1 little r charges. And so why this should enhance to an SU2 is like totally mysterious. We have no sort of physical reason for the existence of this USP2. There's some speculative things with relation to like S duality that I could say, but we have no clue really what this thing is. And right in time, I want to thank you for your patience, and I'd like to open the table for any questions.
Okay, let's thank Nick. So are there questions?
Hello.
Well, hey, how does this extend beyond gauge theories? The
Which
structure,
part?
well, for instance, the analogy to the cohomology of Kähler manifolds and the Q plus Q minus lemma and things like this, and the formality result.
So
or can it be tested on some examples?
That's yeah. So I would imagine there might be some issues that stem from the fact that if you look at the anti-commutator of Q1 and Q2 in the physical theory, it's not 0. And so one of the sort of features is that like D and DC anti-commute with each other. So like in this n equals 4 super quantum mechanics, you have like Q1 and Q2 actually anti-commuting with each other. And the reason why this isn't a problem with the superconformal gauging examples I was talking about is because when I'm looking at sort of Schur operators in the weak coupling limit, this is sort of already satisfied for like in like the free field theories, for example. And when I turn on the gauge coupling, these are quantized, like the U1 little r and spin are quantized numbers, and so they can't flow. And so when I'm looking at sort of Schur operators in the weak coupling limit, they do actually have this equal to 0. And so the fact that these guys actually anti-commute in the vertex algebra is not present in the physical theory. So I'm, in my heart of hearts, I want to say yes, but I don't see exactly how it should work. It seems very close, but one would need to be a bit more careful.
Okay, thanks.
Yeah, of course.
I have a question about this gauging procedure that you mentioned.
Yes.
So what happens here if you take a discrete group? Like you take the free hyper, you want to gauge some discrete subgroup of SU2.
Yeah, this is just going to be an orbifold.
So there is a notion of this for the VOA as well. Like,
yeah, totally.
Okay.
Yeah.
Cool.
Of course, it's not this like BRST procedure because there isn't like a current that generates finite
exactly.
symmetries.
That's
But
not
yeah, it's an orbifold.
Cool. Are there more questions? Okay, I would say let's thank Nick again. And we can go off the record.